Video course on statistics. From basics to advanced subjects. Dr. Yehia Elmogahzy, Professor Emeritus at Auburn University, Alabama, USA. Former Dean of Science, Technology, Math, Engineering at Ocean County College, New Jersey. A visiting professor at a number of universities including Rowan University, Keene University, and Montclair University, New Jersey, USA.
Dr. Yehia Elmogahzy is the founder and the president of L-Learning LLC, a consulting education organization.
The subject of this session is sampling techniques. We will cover some of the main techniques used for sampling from populations. That is, taken a few samples from a population, and we will go to Excel and see how we can perform sampling in a very short period of time. Before we discuss sampling techniques, there are some issues that as we mentioned before, the planning and establishing sample structure and all of that have to be taken care of. These are, as we mentioned, are judgmental, and they involve different types of analysis where it requires some brainstorming of understanding the nature of the population and the physical components in the population and how we deal with certain populations. But what we are dealing with now is purely statistical. Before we discuss the different sampling techniques, it will be very important to point out that there may be some errors in sampling. And these errors, as we will see, we will divide it into two types of errors, what we describe as sampling errors and what we describe as non-sampling error. It's very important that we distinguish between these two types of error as we take samples from a population. Let's go and see that via the slides we have. As I just said, there are two types of errors: sampling error and non-sampling error. A sampling error is committed when there is a difference between the data of the sample and the data of the parent population, leading to a difference between the mean of the sample and the mean of the population. When we speak of the data of the population, we're talking about the data of a population obtained if a census is conducted. And as you know, this is sometimes practical and sometimes impractical to cover the whole population. It's defined simply by the difference between the mean of the population mu and the mean of the sample x bar. We need to get familiar with these terms here. When we say mu, we are describing the mean of a population, and when we say x bar, we are describing the mean of a sample. This type of errors is almost unavoidable. It's going to happen. It's always going to happen that you will take samples that will not match in average the population mean exactly. So we have to tolerate that, because the only way to avoid that is to take a sample that's as large as the population, which is practically impossible or very costly. So it's very important to understand that sampling errors are difficult to detect or calculate, because in order to calculate sampling error, we have to know the mean value of the population, which we often don't. And we also need to know that they are often unavoidable. The second type of error is what we call sampling or non-sampling error. This actually should be the focus of our attention when we take in samples, because it results from human mistakes in performing sampling. Errors in data collection, for example, recording, tabulation, sample bias or failure to obtain a truly representative sample, selecting samples that do not meet the purpose of the study. You'll be focusing on how tall the students are in a certain campus, yet you go to the basketball gym and take a sample from there. That will obviously be very biased to the taller students, in fact extremely biased, and it will result in a definite non-sampling error. To illustrate these two types of errors, let's take an example. Suppose an organization typically pays its salesmen an average annual commission of $50,000 with a standard deviation of 10,000. So from their records, they know that the annual commission is 50,000 and the standard deviation is 10,000. A consultant comes and take a sample of 5 salesmen, and assuming it's a random sample, assuming it's a representative sample, and here are the data that he came up with: 1, 2, 3, 4, 5 observations. Now, if we take the average of these observations, that will give us a 49,000. Now, since we already know that the average annual commission should be 50,000, we anticipate it to be 50,000, then as soon as we see the 49,000, we should know that there is some kind of sampling error, okay? Because we know that the consultant has taken a good sample, representative sample, but no sample is perfect. So as a result, we know that typically speaking, the sampling error will be about 1,000, meaning that if you take a sample from this population, you may be off by plus or minus 1,000. It may be 49 or it may be 51, for example. So that is the sampling error, 1,000, calculated directly by mu minus x bar. The luxury we have here is we know mu, we know the population mean, and that's not the case in most situations. But if you know mu, then from the value of mu and the value of x bar, you can calculate the sampling error. Now, to take this example a little bit further here, let's say that the consultant took another sample in which he was intentionally or unintentionally was biased to the lower value of commission. So if we calculate and here is the values of the sample, the new sample that he took. If we calculate the average of this sample, now we're looking at 43,000. Now, remember, when he took a representative sample, the average was 49, and from that we were able to calculate the sampling error of 1,000. But now we have a strange value of 43,000. That is way lower than the anticipated average of the population of 1,000, of 50,000, I mean. So now we have a 50,000 anticipated average, a 43,000 coming from a sample that is biased, and we have now a 7,000 error value. Now, since we already know that the sampling error should not be exceeding 1,000, so if we put 1,000 as the sampling error and we take it out from the non-sampling, the total error, that will give us a 6,000 values or $6,000 of what we call non-sampling error. In other words, in order to be able to calculate the actual non-sampling error, we really need to know the value of the sampling error. Subtract that from the total error, and that will give us the non-sampling error. This is very important, and it's always a good thing to do before you start sampling is to be aware of the possibility of sampling error and non-sampling error. And the awareness here means don't make gross mistakes. Make sure that the sample is representative of the population. Go back to what we discussed earlier as far as planning and establishing sample structure, and follow or try to address the key questions that we addressed. Look at the population. Look at how data are physically obtained via either data acquisition system or manually typed. All of these issues are very, very important, because if we don't pay attention to these things, we will or may be committing a large non-sampling error. And that's what we we need to be worried about. Now let us move into how what are the different types of sampling? What are the different sampling techniques that we can do? Let's go to the slide here. There are three main types of sampling. The first one is simple random sampling. The second is cluster sampling. And the third one is stratified sampling. It's very important to understand that everything we do when it comes to sampling has to be based on randomness or random sampling. However, as we will look at these three categories, we will see that they involve different ways of achieving random sampling. The first type of sampling is simple random sampling. Random sampling means a population from which we take a sample, and by randomness we mean that each member of the population should have an equal chance of being selected in the sample. It also means that the sample should represent a cross-section of the population. In other words, any components in this population will have an equal chance, the same chance of being selected. Okay, this is very important. Let us entertain via Excel how we take a random sample. But before we do that, let me just run this scenario by you. Suppose we have a finite population of 1,000 people, and we want to take a random sample out of this population, say 100 people out of this. The physical approach to do so would be to have the 1,000 people's names or IDs written in a 1,000 different cards. So now we have cards. Each card has the name or has the ID of each person of the finite population. We now have 1,000 cards. We will take those 1,000 cards and shuffle them very well and put them in a box and draw blindly or randomly 100 cards, and that will be a fair sample. Meaning if this withdrawal is for a prize or for selection of some people to do some tasks, the people that are not selected will not complain because they had the same chance and the same opportunity of being selected. It just so happened that the sample was selected randomly, and since the sample was only 100, they were not included in the sample. Same thing like the lottery. I mean, millions of people buy the lottery, and only one winner. Now, other people do not complain. The reason they do not complain that they did not win, although they may be very upset and very depressed because they needed the money, the reason they did not complain is that every member, every person that bought lottery has the same chance of being selected in the drawing of the winners or the winning numbers of the lottery. You can take this situation and apply it to many applications, and you will find that random samples are fair and they are straightforward to do, and they involve minimum complaints. As we will see later on, sometimes they are easier theoretically done than practically. Let's go to Excel and see how we can perform random sampling in a few minutes. Now, recall the scenario we just mentioned. We have 1,000 people. Here is the person ID, and I made it easy here. I start at 1 and I went all the way to 1,000. So we know that we have consecutive numbers here, all the way IDs from 1 to 1,000. And the second column, you don't have to worry about it now. It's really the gender and the race of each person. The female, white. The second category may be male white, and then female black, male black, and so on. But what we're really focusing on here is our IDs of 1,000 people. And in order to take a random sample out of this, and suppose we're going to take 100 people, which is the sample size here. In this case, we go to data, as we did before in performing other analyses, and we'll go to data analysis, and we look for sampling, and here is samples. Then we say OK, and the sampling menu is very simple. The first window in the sample asks you to put the input range, and the input range in this case is actually the people ID. So if I go here and block this entire column of 1000 IDs, then I have given Excel the input. By doing so, I'm telling Excel that this is the finite population from which you can actually select the sample that I want. Did we have labels in the first row or the first cell? Yes. And then the default is a random sample. And since we need 100 people out of this, we will type here 100. So now we have the input of all the IDs, and we need a sample of 100, and we're going to pick an output somewhere in here. Let's go up and see if we can actually put our ID here, our output here, and we click OK, and boom, we have a sample of 100 people selected from this 1000 finite population. And as you can see, the numbers here, they look very random. They are indeed random numbers: 974, 460, 122. You can see 37, 40, 671, 989. All of these, number 3, for example, is picked. Number 24. All of these are random samples. And by comparison with the physical way of doing that, that is having 1000 cards with all the IDs typed on them, and put them in a box and then shuffle them and pick 100 cards. Doing that using Excel in almost a second or two is, in my opinion, a real incredible technique that was provided by the computing power we have today. So that is the way we take a random sample using Excel. It's very important as we do that is to understand the underlying concept of sampling here. Here we are trying to take a random sample, and we can repeat this analysis many times. And trust me, every time you repeat, you will not repeat the sample. To be a different sample with different random numbers taken from the 1000 finite population. Now let's go to the slides again and continue with our subject. In summary, what we did, we had 1000 ID, we went to data, then we went to data analysis, and we went to data analysis sampling menu, and we pressed OK to go to the sampling menu. And in the first window, we put the input range, which is all the IDs of the finite population. We clicked labels because we have labels in the first row, as you can see here. And we selected random, and we put the number of samples we need. We said 100. And we specified an output. And by doing that, we were able to generate a random sample, as I said, in a second or two, as you saw. This is very important to understand, and it's also very simple to do. Now let us move on with the second type of sampling, which is the so-called cluster sampling. Sometimes the population itself is divided into groups, and in this case it may be useful for one reason or another to make sure that we take samples from the different clusters of the population. That is what we mean by cluster sampling. We specify clusters. For example, if we're looking at a larger city, maybe we're looking at some area, downtown versus uptown, east, west, north, south of the city, and this may represent clusters of people that we would like to have taken samples from each clusters. So that's what we call cluster sampling. Keep in mind that in each cluster, the sample taken or the individual components taken still have to be random. So we don't just go to any category or any cluster and pick anybody. No, they have to be also random. Finally, the so-called stratified sampling. In a stratified sampling, we intentionally divide the population into different stratas or different categories. For example, you have a factory that have all the machines, new machines, or 4 different brands of machines. And in this case, we really have to divide the population into these 4 categories or 4 strata, and then we select samples from each category, hopefully in proportional weight allocation to the size of the category. In this slide here, it shows that the 4 categories are equal in size, but sometimes you may have one category that represents 75% and the other category only 25%. In this case, the stratified sampling should actually reflect that. It's very important to know how many should we take from each category in a stratified sampling. That's what we mean by proportional weight allocated samples. This equation here is a very simple equation that will help you calculating the number of components belonging to each category in the sample. So Ni is the sub-sample size of each category. N is the total sample size. N capital I is the total size of that category in the population, and N capital is the total population size. Let's take a quick example here. Suppose we have a finite population of 1,000 people, representing a population of a small city. 240 are female white, 260 are male white, 210 are female black, 290 are male black, and 290 people are male black. What's the number of people from each category should we select? Here is we need a 100 sample size. The population size is 1,000. And here is the pie chart that represent the divisions of each category and the sub-population size in each category. And applying the equation is very simple. If I need to take from female white, then applying the equation, the total sample size would be 100. If I need Ni, or the number of, or the sample size or the sub-sample size of female white, I know that Ni, or the capital N in the population, is 240, and I know the total N is 1,000. Straightforward calculation would say that 100 is the sample size, 240 is Ni capital, 1,000 is N, or the total population size, and now we have 24 coming from this category from the population. And of course, it's easier to realize that because we're talking about 100 taken from 1,000, so 240 by proportional weight allocation will be 24. And if I repeat this for female black, where I have 210, following this equation, I will get 21. And this equation is really useful when you have complicated sample size, 27 or 21. Then it becomes difficult to calculate the proportional weight allocation easily, and in this case you should use this equation. And if you have fractions such as 26.7 or 25.4, then you need to round up these numbers, meaning lean to the upper size of each subcategory to make sure that you have more than you need in the sample. It's always better to have more components than less in taking any sample. This was briefly an overview of the 3 main sampling techniques: random sampling, cluster sampling, stratified sampling, and also how we perform these sampling techniques using Excel. Excel does not have a straight or direct way to do stratified sampling, but since once you decide the subcategory and how many you want from each category, and we said that in each category you have to go and actually select a random sample, you can manipulate Excel to select stratified sampling as well.
Video course on statistics. From basics to advanced subjects. Dr. Yehia Elmogahzy, Professor Emeritus at Auburn University, Alabama, USA. Former Dean of Science, Technology, Math, Engineering at Ocean County College, New Jersey. A visiting professor at a number of universities including Rowan University, Keene University, and Montclair University, New Jersey, USA.
Dr. Yehia Elmogahzy is the founder and the president of Learning LLC, a consulting education organization. You can order a complete set of the course with all video sessions, slideshows, PDF file of the course, test bank, and data bank by visiting Amazon.com.